Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about Propellant Depot or Space Propellant Depot, Space Fuel Tank. So let's dive right into it. Now, what is our problem at this point in time that we need to think about making a quote-unquote petrol pump in space? The first thing is we have to carry fuel for the fuel. Basically, what does that translate to? Think of it this way: if you actually wanted to figure out how much energy it's going to take to basically take off from the moon, come to Earth, land safely on Earth, that's not that much. But here's the deal: then why the heck Saturn V is this huge? Simply because it was carrying everything from day one. Like from the moment it was launched, it's supposed to have everything. So basically, you are using fuel to carry fuel. It's almost like how basically fuel tanker is burning fuel to carry the fuel. Same thing is happening here. Now, to understand it in common day-to-day life, think of it this way: you have a car, but you do not have a petrol pump. How far can you go? As simple as that. Think of this way. Or if you have to go far, let's say from Calcutta to Delhi, or Los Angeles to New York, how much larger your fuel tank has to be. So that makes it easy to understand that why the rockets are basically 90% fuel. That's the primary reason for that. We have good engines, we got rocket technology, we just don't have a goddamn refueling station. So basically, first part of our technology is done. We got the basically cars. We have to build the infrastructure for those cars, like petrol pumps. That's the missing element at this point in time. Now, going to low Earth orbit is one thing. The moment you want to plan something grander than that, for example going to the moon, you need huge rocket. And if you are planning to go to Mars, forget about it. We tangibly can't even dream about making a rocket that is powerful enough to actually go to Mars right now in one go. Flat out can't do. Like 2 years is like sounds okay, but for robotics, from human manned mission, 2 years in space, both way, yeah, forget about it. So fundamentally speaking, that's a very serious problem. Now, there is another side effect. That's for missions. What about space itself? Well, when you are talking about space itself, the primary use of space that we are utilizing right now is for satellites. Now, many satellites that are basically on very high orbit or some weird kind of orbits, they need what we call station keeping fuel. Now, many satellites, things do happen. There are equipments, things do happen. For example, a satellite could have a launch issue where the rocket did not manage to put it in exact orbit. So what will a satellite do in that sort of scenario? It will basically use its station keeping thruster for maximum power and try to correct the orbit. So at least it can give you, let's say, if it was planned for 5 years, at least it can give you 2-3 years of uses. It will try to do its best. Now, what happens after that? Now, it's a car is awesome, it's working, everything is fine, it's making you revenue, but because it's running out of fuel, you inherently have to crash it into Earth. So that creates a problem where we are just throwing things away. Basically, car ran out of fuel and we throw it away. Car ran out of fuel and we disposed of it. So things of this nature happens on almost a regular basis. Like if you talk to telecommunication industry, these things are like, oh yeah, that satellite we have disposed of, this satellite, yeah, we have disposed of, this satellite disposed of. And most of the time it's it's in the planned manner, but surprisingly large amount of time it's for unplanned manner. Basically, yeah, our launch provider kind of messed it up, so we had to burn the propellant and now we are out of fuel, so we have to deorbit the satellite before time or put it in graveyard orbit before time. So that basically creates a scenario where you have way too many satellites that are electrically awesome. They're like, we good, bro, we good, we can keep working for next 5 years or next 10 years, because we do put a lot of effort specifically on geostationary satellite to make them like as robust, as hardcore as possible, and they do have the ability to last. It's just they run out of fuel. It's basically, car is awesome, it's just we don't have fuel tank. So it translates to, like, why does anybody gives a damn? It translates to billions of dollars wasted. Not $1, not $10, not $1 million, not $100 million, billions of dollars wasted annually. So fundamentally, that creates a serious waste issue. Now, let's understand the rocket part of this equation. Now, what will happen if we can actually do this? Now, think of it this way, understand it this way. Let's say Falcon 9 max thrust can put around 15 tons to low Earth orbit if it's going reusable, return to land, super easy, all that jazz. Okay, everything is fine, everything is dandy. What happens at the second stage when you are at that orbit? Let's say low Earth orbit, you are putting 15 tons. What happens to second stage at that point in time? If you think it runs out of fuel, that's absolutely correct, it runs out of fuel. But what would happen if you take the same second stage but you fueled it completely? Basically, not like 10% or 20%, no, complete fueling it. What kind of delta V you can add on this puppy at that point in time? That would be significant amount of delta V can be added. And this also solves another issue. It's like, if you take a rocket, it's like, hey, how much it can put to low Earth orbit? 22 tons. Yeah, baby. How much can it put in geostationary? It's like 8 tons. Why did it went down? Simply because it does not have the fuel. Now, you take to low Earth orbit, you refuel it in low Earth orbit. At that point in time, this puppy is like, I got this. I can go wherever you want me to go. Like even a small rocket like Falcon 9. Yes, I'm talking about small simply because we are planning to Mars mission. Yeah, this puppy in comparison is small. So in this those sort of scenario, this puppy will be easily able to carry much higher tonnage to geostationary, to moon, or to even to Mars. At least throw to Mars at much higher delta V's. So fundamentally, there is another benefit to this. Building a smaller rocket is exponentially cheaper. Think of this way. Let's say you are thinking about a rocket, let's say that cost 20 tons for $20 million. Awesome. You may be like, okay, for 100, I should pay 100 million. No. For 100, you have to think about like, 600 or 700 million, because rockets go exponentially higher, because the cranes, the bulldozers, the landing, basically launch pad, everything else, the amount of infrastructure, the amount of material is consumed, it's exponentially more. And not to mention, you also have to figure out ride sharing and all that jazz if you want to make it financially viable. So fundamentally speaking, rockets, if they are small, they are exponentially cheaper compared to a big one. And if you're, instead of launching a big one, you can utilize the small one to do the big one's work. Why would you want to build a big rockets? That's the important aspect for this. So at this point in time, we have learned this the hard way, that we have to make rocket reusable. Now there is another aspect of it. Right now, our payload to low Earth orbit capacity is not that great. And when you are talking about something as huge as starships, you are still talking about launching your starships 5 or 6 times in order to refuel another starship. So flat out, that's why depots are so important. Like we can try to use this, and this will make amazing thing. If you want to use this big puppy to launch these small puppies, then it's going to do amazing things. We can do really amazing missions very far out. But if you want to send large payload capacity, we need bigger depot than this. So that is a very serious aspect about this. Now the biggest benefit of this, once we can do that, once we can refuel basically second stage in orbit, Moon and Mars becomes easy. It's like, bro, we don't even think about it. It's like it will go back to same way now how we are thinking about low Earth orbit at this point in time. So this is about rockets. So now let's talk about Propellant Depot. Now Propellant Depot, what does it has to actually do? Well, first it has to keep cryogenic propellant for long term. Now this is a very serious risk. We do not use cryogenic fluids in day-to-day life for one simple reason. They are not long lasting. Even rockets, they are specifically built for that. They are only able to handle this puppy for a few minutes, or sometimes best case scenario 1 or 2 hours. Or if you are connected to launch pad and your rocket is getting delayed, you have to keep replenishing it. That's not acceptable when you are in space. So fundamentally, we have to think it in long term. Basically, we put fuel here, it's not gonna evaporate away. Now thankfully it's easy to do in space simply because there is no convection. However, there is a lot of radiation. Thankfully, making radiation shield from sun's radiation is super easy, simply because our sun is very bright in infrared rather than being bright in X-ray or gamma rays. It's very bright in infrared. We can stop infrared very easily using world file. That's why the James Webb telescope can have such a large sun shields, which are like very thin shields. Just like you have 5 sheets and it's like, bro, I got this, we can stop the sun. So that's what we have to think about. Basically, these things have to hold the cryogenic propellant for very long time. Now, what in terms of subsystems it needs docking mechanism. So basically, you have to have a way to dock this. Thankfully, we have already figured this out, because International Space Station is it was a very good test bed for testing this sort of technology. And International Space Station does have thrusters which are used for orbit raising, and it is fueled by basically Progress spacecraft. So we have figured this part out. Then we have plumbing. Again, we have already figured it out. And station keeping. Now in olden days, we only had basically rocket thrusters, so it was like very brute force, like push and then you wait, push then you wait. Now thankfully we have ion engines, so we can do it much more gently and much more controlled manner. And the technology is being tested out with Starlink satellites on Mars. So fundamentally, not that complicated of a technology. And basically, many times people think, okay, we have to build something huge like International Space Station to get started. No. This is the interesting part of it. We can start small. Basically, target should be something very small, something that we can just prove out the concept. Basically, boost smaller rocket capabilities. That's the first goal. Then you plan to, okay, now we have boosted basically, let's say Falcon 9, then figure out how to boost basically Starship. Don't directly go to Starship, start with Falcon 9, then it's like, okay, go to this system. So bigger depot will allow you to have bigger capacity. That will allows you to have much bigger payload capacity. Basically, if you want to throw, if your main goal is basically send something to Mars, a bigger fuel depot is not necessary. You can utilize a small rocket as long as you can your payload mass can actually go to orbit. That's all you have to figure out, and that's surprisingly cheap. Like if you ask anyone, 20 ton to low Earth orbit, that's not that expensive. 20 ton to Mars, yeah, forget about it. So fundamentally, that's you have to think about. It's like we can start with small. We do not have to be like, okay, let's build another international space fuel station, then we start doing big things. No, we can start small. And I mean, how small? Something that can be done with SLS, basically Starlinks, or even Falcon 9 if you really want to do that. And there are designs that are utilizing Vulcan engines, Vulcan rocket upper stages and all that jazz. So it is something that can be done without requiring some magical technology. It is something that we can be done, and the prime candidate at this point in time for rockets is basically liquid oxygen and methane. The primary reason is that even though you may want to utilize hydrogen in those environments, hydrogen has this bad tendency of just basically go through material. You can have a wall. Now, unless you have a very thick wall, hydrogen has this ability to just go through material. Like you can have a flat out metal wall and it can just like, nope, it can simply nope through it. So fundamentally speaking, nobody likes hydrogen. Like sealing up hydrogen is very difficult, and given its temperature, even the small amount of radiation that will make into your tank, it will start to boil it off, and that makes it like a much more harder. You have to run much higher end heat pumps to keep it at cryogenic temperature, while liquid oxygen you cannot get away from. Like you have to know how to keep liquid oxygen. It is much more forgiving comparatively speaking, and if you can keep liquid oxygen, keeping liquid methane is much more simpler. So basically, for let's say you put 100 tons of both, you have 100 tons of both those puppies. Let's say your heat pump for oxygen comes up, let's say once every day. It's like every 24 hour the pump comes up just to reduce the temperature. For methane, it has to come up like once every 4 or 5 days. So that's why for Propellant Depot, first you have to figure out a tank installation so it lasts longer. Then you have to have docking, plumbing, and station keeping. Then you will start small, like just like a big payload. Then it's launching smaller payloads, and then we can start keep making bigger and bigger depot. That will expand our final capacities. Basically, how big can we actually do this? And liquid methane is the best option at this point. There are other companies that are already working on basically making satellite repair bus, quote unquote. So basically they have a trolley system, not trolley, basically it's just like a main bus. This main bus has the ability to fuel and do everything, and then these small blocks, they are basically quote unquote independent. They will detach, go to a satellite, fuel that puppy up, and then come back on the main bus, and then main bus will be like fueled by the main craft. So instead of launching these small refillers every rocket, you will launch this whole system in one go, and this puppy will have the ability to refuel multiple satellites in one go. And once it's depleted the fuel, you're only gonna detach the big fuel tank part, and then you're gonna connect another fuel tank. So this puppy can keep doing this. There is a very amazing presentation about this linked down below. You should check it out. That's the Propellant Depot idea. So for satellites, we're gonna have something different, because many times satellite do not want to use cryogenic, they want to use hypergolic. So you want to utilize that puppy. And for rockets, main big ass rockets, we have to use cryogenics. Now, what we can expect in the future? Now, this is one of those things where it's becoming inevitable, even though there was a senator who's trying to block this. Now, for good reason, because people elected him like, hey, keep our job. And he knew for a fact that if propellant depots are actually made, all the big rocket companies, they're gonna go poof. So fundamentally speaking, he was doing a good job. People elected him for that. But we have to do this sooner or later. We have to do it. Same way like that whole concept that was put on ice is brought back to fold. It's simple as that. We have to do this. This is not optional. This is not something that we can postpone. We have to do this. And even SpaceX, they were like not that excited about refueling. The flat out, it's like, dude, we can't send 150 ton to Mars unless we refuel our goddamn rocket. There is no other way. There is no other option. We can't even conceive of a rocket that would be powerful enough directly to do that from Earth. We have to refuel in orbit. And even they realized like this puppy is a big task. Refueling in orbit, something as big as Starship. Now for going to moon and back, oh, that's easy. That's chump change. For going to Mars with proper fuel load, yeah, good luck with that. Like that's why their mathematics is bare minimum like 5 launches of a tanker system to fuel that puppy up. Now, why would anybody want to invest in this sort of system? Because these are big, complex things. We may be talking about like once we are actually, every country is on board, we are talking about another international fuel station. So what will be the final benefit of it? First, cost, money. Every Tom, Dick and Harry cares about the green, and it will save a lot of money. So flat out there is that. Another aspect, it will also save missions, because if you right now you want to do ride sharing, and if you have just let's say CubeSat, but you want to send that CubeSat to moon, you can do that utilizing gravity assist and all that, but it's gonna take like months, upwards of 6-7 months. So time is money. So if you can refuel your even tiny rocket, you can easily send that puppy to moon in like 3 or 4 days rather than 3 or 4 months. So not only it saves money, it also saves time. Both of them are big enough reasons that people will do that, like both of them. And this will allow much more grander missions that we can't even begin to imagine at this point in time. And it's inherently not that complex of a thing, because it's like all you are talking about is fuel tank, and basically ULA already figured out like more of the core studies that you have to do before you get starting building. They have already done that. And prototyping, we already know we have upper stages that go into orbit, which has liquid fuel and restarting capabilities. We know that, like we have some ideas how to do that. It's just that we have to extend the duration. It's like, oh, it can stay in basically low earth orbit for like, let's say 5 hours, 6 hours. We have to just stretch that to, for first few times, only a week, so we can launch the system, second rocket, and then we test out the system. Of course, over time we're gonna just like keep extending. So first time every propellant depot was tested for 1 week, then it will be 1 month, then it will be 1 year. So we have to do this. This is not optional technology. This is something we have to do. Sooner or later, today or tomorrow, we're gonna build this. So this was my presentation on basically space fuel tanks. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.